Welcome to the deep dive. Ever wondered what makes some materials, incredibly strong, heat-resistant, maybe even sparkly?
Mm-hmm.
Today, we're diving deep into the world of alumina, that's aluminum oxide, or aliro, and it's a fascinating family of related compounds.
Yeah, it's a really core material.
Think of this as your shortcut to understanding why this seemingly simple substance is actually a cornerstone of modern tech and even natural beauty.
And to guide us, we're digging into the insights from ceramic and glass materials.
Yeah.
We're focusing on the chapter all about alumina, plus later discussions on related materials.
Right.
And it's worth mentioning, this comprehensive work is dedicated to Professor Robert H. Doremus, a real pioneer in the field.
Okay.
His work at GE and Rensselaer Polytechnic Institute, especially on the alumina-silica relationship and early bioceramics, well, it really laid a lot of the groundwork for what we know today.
Okay, let's unpack this then, starting with alumina itself. It's often called the structural ceramic. What makes it so, fundamental?
Its importance really comes down to a remarkable combination of properties. It's frankly quite unusual.
Okay.
First off, think about its melting point, a staggering 2054 degrees Celsius.
Wow.
That, plus its exceptional chemical stability, means it can handle incredibly high temperatures without, breaking down or reacting.
Right.
So that makes it crucial for everything from components in industrial furnaces to the platforms that hold catalysts in chemical reactions.
Industrial furnaces, got it. But you also mentioned biomedical implants. That seems like a bit of a jump.
Well, what's really fascinating is alumina's inertness inside the body. It just doesn't tend to react with bodily fluids or tissues.
Biocompatible.
Exactly. It's biocompatible. Your body pretty much ignores it, which is exactly what you want for an implant.
Makes sense.
And beyond that, it's sheer hardness, high strength, and incredible resistance to being worn away. That makes it invaluable for things like abrasives, for grinding and polishing. Also bearings and machinery that face constant friction, and the super tough edges on cutting tools.
So it can do the grinding and resist being ground down itself.
That's powerful. And I think I remember reading it's key in electrical stuff, too.
Absolutely. It's very high resistance to conducting electricity, makes it a go-to material for electrical insulators, stops the current where you don't want it.
Okay.
But there's also a visually stunning side. In its purest form, it's actually optically transparent.
Really?
Yeah, and when you add tiny amounts of certain elements like chromium or titanium into its crystal structure, boom, you get the vibrant colors of gemstones.
Like rubies and sapphires.
Exactly, rubies and sapphires. In fact, a ruby crystal is even used as the heart of some lasers.
Wow, from industrial grit and grind to sparkling gules and high-tech lasers, that's some range. I even have this vague memory of it being used in street lamps.
You're right. The intense arc inside some high-intensity streetlights needs a container that can handle extreme heat, won't react chemically, and lets the light shine through.
And alumina fits the bill.
Perfectly. High melting point, inertness, transparency, it's got it all for that job. So where does all this versatile alumina actually come from?
The source material points to bauxite ore. You find it in places like the Guianas, Brazil, parts of the southern U.S., Southeast Asia, West Africa, India. Quite widespread.
And there's a specific process to get the pure alumina out, right?
Exactly. The Bayer process, that's the workhorse for extracting alumina from bauxite. It's a chemical process that cleverly separates the aluminum oxide from all the other stuff in the ore, like iron and silicon compounds.
Okay. Now, zooming in a bit, at the microscopic level, alumina isn't just one single structure, is it? I remember reading about different phases.
Okay, yeah, here's where it gets really interesting. The most stable form under everyday conditions, normal pressure, normal temperature, is called corundum, or alpha. Right. And in its single crystal form, that's what we know as sapphire.
Okay.
And get this, it's incredibly tough under pressure. Experiments show it stays in this corundum structure, even up to a mind-boggling 175 gigapascals.
That's huge pressure, right? Like deep inside the earth.
Exactly. Scientists even think it would only transform into other structures at even greater, almost unimaginable pressures.
So that arrangement of aluminum and oxygen atoms is just inherently super stable?
It seems so. But most alumina we actually use isn't single crystal sapphire, is it?
No, right. The alumina in most structural things is polycrystalline. Think of it like a mosaic. Lots of tiny alumina grains all bonded together.
Mhm.
And that's typically made by taking fine alumina powder and heating it up really high in a process called sintering.
Like fusing the powder particles together.
Yeah, imagine heating sugar crystals just enough so they stick together into a block. Similar idea, but way hotter for alumina.
Okay.
Then you also have these things called metatastable phases, gamma, delta, and theta alumina.
Metastable, meaning less stable than the alpha form.
Exactly. These are less dense than corundum, and their oxygen atoms are arranged in ways that are close to cubic close packed. Think of stacking oranges on a fruit stand, that kind of efficient packing.
Okay, so different arrangements. And these metastable ones, gamma, delta, theta, they don't just stay that way, do they?
Nope. As you heat them up, they tend to transform. There's a typical sequence. Gamma usually goes to delta, then delta to theta, and finally theta settles into the most stable alpha phase, the corundum.
So it's like steps towards stability.
Kinda, yeah.
Yeah.
But it's not always perfectly rigid. Things like how big the starting particles are, how fast you heat them, any tiny impurities, even the atmosphere around them, they can all nudge the sequence and the temperatures where the changes happen.
Ah, so the conditions matter.
They do, but once you get above about 1200 degrees Celsius, you're pretty much always going to end up with just the stable alpha phase.
It's like a dance of atoms influenced by their surroundings.
Now, what about how alumina interacts with other materials? Does it dissolve easily?
Generally, no. Alumina isn't very soluble in water or other common oxides. That resistance is a big part of its stability.
However, and this is a bit surprising, it can form mixtures with certain other oxides. Things like vanadium pentoxide, bismuth oxide, tungsten trioxide, boron oxide.
Right.
And these mixtures can have surprisingly low melting points. They're called eutectics.
Eutectics, okay.
For example, the eutectic mix of alumina and vanadium pentoxide melts way, way below alumina's own melting point, just 660 degrees C.
Wow, that's a huge drop. Really shows how combining materials can totally change their behavior. Let's shift gears a bit. How does alumina handle physical force? Its mechanical properties.
Right. Alumina is a classic brittle material.
Brittle meaning it snaps.
Yeah, exactly. If you push or pull on it, it stretches or deforms linearly, following Hooke's law, right up until crack. It fractures suddenly without much bending or warning. Think of dropping a ceramic mug.
Shatters, doesn't bend. Got it.
And its stiffness, what scientists call its Young's modulus, is very high for polycrystalline alumina, much higher than most other oxide ceramics.
Why so stiff?
It's down to the incredibly strong chemical bonds between the aluminum and oxygen atoms.
Ah, the bonding.
Though, interestingly, this stiffness does decrease a little bit as it gets hotter. The atoms vibrate more, weakening those bonds just slightly.
Okay. And how does it handle heat itself? Thermal properties.
Well, its density varies a bit depending on the phase, alpha versus the metastable ones. And related compounds like aluminum hydroxides have different densities too. Alpha alumina has a relatively low coefficient of thermal expansion.
Meaning it doesn't expand much when heated?
Exactly. It doesn't expand or contract a lot with temperature changes.
Yeah.
That's crucial, where you need things to stay the same size even if temperature fluctuates.
Right, dimensional stability.
It also has a significant specific heat capacity. It can soak up a fair bit of heat without its temperature shooting up too fast.
Okay.
And its overall thermodynamic properties, like how much energy is stored in it, they change predictably with temperature. It also has a very high boiling point, way up around 35-30 Celsius.
Yeah.
And it takes a huge amount of energy, the heat of vaporization, to turn it into a gas. Even more energy, proportionally, than it takes just to melt it.
So tough to melt, even tougher to boil off. How well does it conduct heat?
Single crystals of alpha alumina are actually quite good thermal conductors. Really, I thought ceramics were usually insulators.
They often are, but pure sapphire is different. In materials like this, heat is mostly carried by lattice vibrations called phonons.
Phonons, like packets of vibration energy.
Kind of, yeah. Think of them zipping through the crystal. Alumina's ability to conduct heat depends on how far these phonons can travel before bumping into imperfections or other phonons. Temperature and crystal purity affect that distance.
Okay, moving on to electricity, we said it's a good insulator. Is that the whole story?
For pure, dry sapphire, that single crystal alpha alumina, yes, the conductivity is very low. But it does increase as the temperature goes up.
Ah, so it's not a perfect insulator at high temps.
Not perfectly, no. Scientists see alumina as a wide bandgap semiconductor. At really high temperatures, electrons can gain enough energy to jump across this energy gap, allowing for what's called intrinsic conductivity.
Or intrinsic. from the material itself.
Right. And at lower temperatures, any tiny impurities in the crystal, maybe a bit of silicon, can donate or accept electrons. That leads to what's called extrinsic conductivity.
So even tiny impurities make a difference electrically. What about magnetism?
Alumina is diamagnetic.
Meaning?
It has a very weak repulsive interaction with magnetic fields. It's definitely not magnetic itself. In fact, it tries to slightly push magnets away.
Okay, not magnetic. And what about atoms moving around within the alumina? Does diffusion happen?
Yes, diffusion, the movement of atoms or ions through the material does happen, although often quite slowly, especially lower temperatures.
Right.
The rate it happens is strongly influenced by temperature.
Okay.
You can describe it mathematically with the Arrhenius equation.
And why is diffusion important here?
Well, it's crucial for understanding how alumina powders sinter together to become dense ceramics. It also relates to how alumina might slowly deform under stress at high temperatures, a process called creep, and how impurities might gradually move through the material over time.
I see. And it has dielectric properties too, you mentioned. How it behaves in electric fields.
Yes, sapphire has a dielectric constant. That's a measure of how well it can store electrical energy when you put it in an electric field.
Okay.
And this constant isn't fixed. It changes depending on both the temperature and the frequency of the electric field you apply. That's important if you're using it in capacitors or other electronic components.
Makes sense. Finally then, chemical reactivity. How does alumina interact chemically?
Generally, it's pretty inert, chemically speaking. It doesn't readily react with common nonmetals like chlorine, bromine, or iodine. Fluorine is an exception that's very reactive and will react with alumina.
Okay. What about metals?
With metals, you can use a thermodynamic concept, Gibbs, free energy, to predict if a metal is likely to displace aluminum from alumina in a reaction.
Like steal the oxygen away.
Essentially, yes. For example, calculations show that yttrium will react with and reduce alumina at high temperatures because the energy change for that reaction is favorable.
Interesting.
It's also interesting to look at the equilibrium it sets up with gases like hydrogen, water vapor, CO, CoROs at high temperatures. The balance between alumina and these gases depends specifically on temperature and pressure.
And bringing it back to the visuals, those amazing colors in sapphire gems, that's not pure alumina, is it?
Exactly. That magnificent deep blue of sapphire comes from tiny traces of iron and titanium impurities mixed into the alumina crystal.
Impurities causing color. How does that work?
It's a process called charge transfer. Basically, when light hits the crystal, an electron can jump from an iron ion to a nearby titanium ion, or vice versa.
Okay.
This electron jump absorbs light energy, specifically in the yellow-orange part of the spectrum. And when you remove yellow-orange light from white light, what's left looks blue.
Ah, subtractive color.
Precisely. And different impurities or combinations can absorb different wavelengths, leading to the whole rainbow of colors you see in sapphires and rubies, both natural and lab-grown.
Fascinating. So alumina is this incredibly versatile material, just amazing properties and uses. Now let's look at some of its close chemical relatives, the aluminosilicates, starting with mullite.
Mullite, right. Its chemical formula is often given as 3Al euro, 2 but sometimes you see 2Al euro.
What's the difference there? Is it two different things?
It's a bit complex. The exact ratio of aluminum to silicon in mullite is still debated a bit at the finer points. The 3.2 form, 3 alumina to 2 silica, is generally seen as the most stable.
Okay.
But the 2.1 form seems to exist as a metastatable phase, maybe stable at lower temperatures. Under certain conditions, like really high heat or repeated heating, some alumina might even separate out of the mullite structure. And whether you start with alpha alumina already present in your mix can influence the final mullite you get. Interestingly, deep in the earth, under huge tectonic pressures, silica can actually get squeezed out of mullite, forming minerals with a 1.1 ratio. Those are the sillimanite minerals we'll talk about next.
Wow, so conditions can really shift these structures around. How do people actually make high-purity mullite for use?
There are several ways. One is to melt alumina and silica together, often near that 2.1 ratio, and then control the cooling very carefully so mullite crystals form.
Okay.
Another way uses starting materials with more alumina, melts them, and then quenches it, cools it really fast to get a glass. Then you heat that glass gently to crystallize the mullite.
So melt cool or melt quench heat.
Right. You can also just start with fine powders of alumina and silica, mix them really well, and heat them to react maybe 1200 C or so to form mullite. Then you heat them more, sinter them to make a dense solid piece.
Powder route, any other methods?
Yeah, more advanced ways too. Combustion synthesis, you mix precursor chemicals that rapidly burn, leaving behind fine mullite powder.
Burns to make ceramic. Cool.
It is. And sol gel methods are also important. These let you mix the starting materials incredibly well, like at a molecular level in a liquid, which then turns into a gel, and finally you heat that to get very pure mullite with really controlled
So
properties.
gold gel.
Yeah.
Sounds precise. So what are the key properties of mullite itself that make it useful?
Well, mullite has this interesting defect structure in its crystal lattice, and that actually leads to relatively high ionic conductivity, especially for oxygen ions at high temperatures.
It conducts ions.
Oxygen ions, yeah. In fact, its oxygen conductivity can even be better than some common solid electrolytes like calcium-stabilized zirconia, which are used in things like fuel cells.
That's surprising.
It is. Scientists have measured how fast oxygen atoms diffuse through mullite, and they found that diffusion along the grain boundaries, the edges between the tiny mullite crystals, is much faster than through the middle of the crystals.
Faster pathways at the boundaries. What about mechanically? Is it strong?
It has good fracture. Toughness resists cracking, pretty good flexural strength, which is resistance to bending, and decent micro-hardness. And these properties hold up reasonably well even when it's hot.
Okay.
Plus, its low thermal conductivity, it doesn't transfer heat easily, and its low thermal expansion make it excellent for refractory applications.
Refractory, meaning high temperature stuff again.
Exactly. Materials that need to withstand extreme heat without melting, deforming, or letting too much heat pass through. Furnace linings, kiln furniture, that sort of thing.
Makes perfect sense. Now, you also mentioned the sillimanite minerals earlier, another group of aluminosilicates.
Yes, andalusite, kyanite, and sillimanite. These three are polymorphs.
Polymorphs. Same chemical formula, different structure.
Exactly. They all have the same formula, LCO, 1 alumina to 1 silica, but the atoms are arranged differently in their crystals. What's geologically interesting is that these aren't the stable forms of LCO or at normal atmospheric pressure, like here on the surface. They form deep inside the Earth under high pressure and high temperature.
So we find them in rocks, but they wouldn't just form if you mixed alumina and silica in a lab at room pressure.
Correct. They can hang around for ages metastably in rocks, but they formed under much more intense conditions. The key difference in their structures is how the aluminum ions are coordinated by oxygen atoms.
Coordinated? How many oxygens are around them?
Precisely. In andalusite, some aluminum ions have 5 oxygen neighbors. In kyanite, all aluminum ions have 6. In sillimanite, they also all have 6, but the overall arrangement of how those groups link up with the silicon tetrahedra is different from kyanite.
Different structures, different coordination.
Right. And kyanite has a triclinic crystal system, while sillimanite and andalusite, like mullite, are orthorhombic.
Okay. And what happens if you take these natural minerals and just heat them up in normal air?
They all decompose. They transform into 3.2 mullite and silica.
Ah, they turn into mullite.
They do. Interestingly, the 2.1 mullite doesn't seem to form directly from this decomposition. And the type of silica you get can vary depending on which mineral you start with.
And do they all decompose at the same temperature?
No, that varies too. Kyanite starts breaking down lowest, maybe around 1150 C, and lucite is next, about 1250 C. Sillimanite holds out the longest, starting closer to 1400 C.
So sillimanite is the most heat-resistant of the three.
Before decomposition, yes. And the temperature range over which they fully convert also varies. These temperatures can even shift a bit depending on where the mineral came from geologically and what impurities it has.
And since they turn into mullite when heated, that must be why they're mined, right?
Precisely. There are major kyanite deposits in places like the US and India. Sillimanite comes mainly from India and South Africa. Their main industrial uses as a source material, you heat them up to make mullite, which, as we said, is a super important high-temperature refractory.
Got it. Okay, that covers the aluminosilicates well. Now let's broaden out to the wider category of aluminates. What defines these?
Aluminates are basically a diverse family of compounds formed when alumina, LeOro, reacts and combines with oxides of other metals.
So alumina plus something like calcium oxide or magnesium oxide.
Exactly. These combinations can form both glasses and crystalline ceramics, and they have a huge range of uses. Traditional ceramics, advanced optics, even biomedicine.
Okay.
A key group is the alkaline earth aluminates, like calcium aluminates you mentioned. They're important in some refractories and are chemically related to Portland cement.
So it's like alumina teaming up with other oxides to create new materials with maybe different properties.
That's a great way to put it. Many aluminates inherit key traits from alumina itself, like being refractory, having high melting points.
Still heat resistant.
Very much so, and often hard, strong, and chemically resistant too. But the combination can bring new properties. For instance, some aluminates, especially with calcium or rare earths, can be transparent to infrared light.
Infrared transparency, useful for IR optics.
Exactly. Things like infrared optical fibers or windows.
Let's dive into some examples. You mentioned calcium aluminates.
Right, the CLL system. Its
Yeah.
phase diagram, the map of stable phases at different temperatures and compositions, is pretty complex.
Okay.
You've got the high melting ends, pure CaO and pure aluro, but there's also a deep eutectic point. Remember eutectics?
The lowest melting point mixture.
Right. That lower melting point can be useful for processing these materials.
Right.
And there are several distinct crystalline compounds that form between CaO and aluro at different ratios. Some hydrated forms of these are the active ingredients in certain types of high-performance cements.
Interesting. What about magnesium aluminate?
The MgO-aluro system is a bit simpler. The phase diagram shows only one stable intermediate compound forming between magnesium oxide and alumina. That's spinel, MgAl-euro.
Spinel, is that like the gemstone?
Related, yes. Spinel has a very characteristic crystal structure. Typically, magnesium ions sit in tetrahedral sites, surrounded by 4 oxygens, and aluminum ions sit in octahedral sites, surrounded by 6 oxygens, all within a close-packed oxygen lattice.
Okay, specific structure. Lithium aluminates were also mentioned.
Yeah, the LiO-Al-Era system. Again, you have the high-melting lithium oxide and alumina at the ends, and 3 stable compounds form in between at specific Li-to-Al ratios.
Any special uses for these?
They're being heavily researched for potential use in next-gen fuel cells because they can conduct lithium ions.
Ah, ion conductivity again.
Right. Also potentially in nuclear fusion reactor designs because they can be used to breed tritium, which is a fuel for fusion.
Wow, fuel cells and fusion. Now, yttrium aluminate and Ig, that sounds particularly high-tech.
It is. The IORIO system, yttrium oxide and alumina, has been studied extensively. Its phase diagram is quite rich, shows 5 different crystalline compounds forming. Yeah. But the star is yttrium aluminum garnet, YAR.
YARO, why is it so important?
Because high-quality single crystals of YAG are the workhorse host material for many solid-state lasers.
The heart of the laser, like the ruby example earlier.
Exactly. These crystals are usually grown from a melt using a sophisticated method called the Czochralski technique. You dip a seed crystal in and slowly pull out a large, perfect single crystal.
So controlling that YALO system is key for making good lasers.
Absolutely. Understanding the phase diagram, knowing exactly which phases are stable where, is crucial for growing those defect-free crystals. There's even a miscible eutectic in this system, which can affect how the YAG crystals first start to form.
Okay.
And another weird thing, if you take molten yttrium alumina and cool it super fast, you can sometimes skip crystallization and get an undercooled liquid.
A liquid below its freezing point.
Yeah. And in this system, that undercooled liquid can do something unusual. It can form a low-density amorphous phase, basically a glass.
A YI glass.
Pretty much. And the way the aluminum and yttrium ions are coordinated by oxygen is different in that disordered glass compared to the ordered YI crystal.
Different structure, different properties, presumably. I also saw a mention of real glass. What's that?
Real glass is a commercial type of single-phase aluminate glass. Originally, they made it using levitation melting, floating the material in a gas stream while melting it to avoid contamination.
Containerless melting. Cool.
Yeah, but now they've developed formulations you can cast in platinum crucibles, which is more practical for production.
And what's special about these real glasses?
They're known for being hard, strong, chemically stable. And you can dissolve high concentrations of rare earth ions in them.
Ah, for optical properties.
Exactly. So they're used for things like infrared windows, optical components, maybe an alternative to sapphire in some cases. And they also have potential medical uses.
Medical? How?
Well, the yttrium in these aluminates can be made radioactive. And that radioactive yttrium can potentially be used in targeted cancer therapy.
That's incredible. From laser hosts to potential cancer treatment, aluminates really cover a lot of ground.
They really do.
Yeah.
And you see other binary aluminates too, like magnesium spinel, used widely as castable refractories for high-temp industrial stuff. And various rare earth aluminates, doped with things like neodymium, are used as scintillators materials that light up when hit by radiation and, again, as laser hosts for different colors of light.
Yeah.
The whole aluminate family really shows how you can take a fundamental material like alumina, combine it cleverly with other metal oxides, and engineer materials with specific optical, electrical, or structural properties for all sorts of demanding applications.
Well, this has truly been a deep dive into alumina and its extended family, we've really explored its core characteristics, the diverse forms it takes, and that astonishingly wide range of applications from, the everyday stuff right up to the cutting edge.
Absolutely. And as we think about this incredible array of properties and uses we've covered, it really does bring up an interesting question for you, the listener, to ponder. Given everything we now know about these alumina-based materials, what exciting new innovations do you think might emerge from exploring them further, from manipulating them at a fundamental level? Especially thinking about fields like energy, advanced medicine, next-gen manufacturing. Where could these materials take us next? The potential feels, well, almost limitless, doesn't it?
A really thought-provoking question to end on. If this deep dive into ceramic and glass materials has sparked your curiosity as much as it has ours, we definitely encourage you to delve further into the source material we mentioned and just the broader field of ceramic and glass science. It's a truly rich and rewarding area. Thanks for joining us on the deep dive.